Okay, so the objective of today's lecture will be probably not the completion, but at least moving forward with respect to the exercise that we have started a couple of weeks now. So it's been some time since last time. So the idea basically is to try to see in practice what are the use of all those theoretical quantities and concepts that we have been developing so far, in particular for the modelization of the motion of a deformable body undergoing large displacement and rotation. In particular, if you remember, we were starting with this example of the typical simple multi-body system composed of a slider crank mechanism. This was composed of 4 bodies, as you can see here in this image, and 3 of them, were deemed to be rigid, so there was no deformation possible for these 3 bodies. In particular, they were the body 1, 2, and 4. So the link connecting all the mechanism to the ground, so body number 1. Then the shaft, OA, body number 2, was rigid as well. And the mass, of course, 4, was deemed to be rigid. What we, in fact, instead considered to be elastic was the body number 3, so the connecting rod AB. This is a typical situation that you can encounter in multi-body systems, meaning that when you will deal with systems of multiple bodies, not all of them will be typically rigid or deformable, okay? And you actually will see this in our conclusive lecture of the seminar on the software add-ons. You will see that not all of the bodies will be considered to be flexible or rigid. Why? Because when you, of course, consider a body to be deformable, we have seen that this involves a certain degree of complexity. You have to introduce so many more variables, all the deformable variables, to be able to describe the deformability of the body. And for certain bodies, this may not be required. Okay, a rigid body description may be sufficient. So there is no need for, in that case, okay, to increase the complexity of the study. So the typical scenario that you will have to face when dealing with a system of multiple bodies is a mixed condition of both rigid and deformable bodies. What we had here was the first decision that we had to go through to characterize the behavior of this deformable body, because again, we repeat, the task of this exercise was to characterize all the quantities that we have defined for this deformable body number 3. So the first question we had to answer was, okay, how do we want this body to behave in terms of physics? And this is something that is up to the designer to choose. Okay, how do we want the physics of this body to be represented? Meaning that, for example, if we have, and this depends, of course, on what, for example, on the geometry of the body, or on the loads. Depending on this information, you either choose one or another physical model to adopt. For example, if you know that this body, number 3, this beam, will undergo small deformation, probably a linear model will be enough. Okay. Otherwise, if you know that it's a very slender body, so very thin and very elongated, and it may undergo large deformation. I'm not talking about rigid motion. I'm not talking about displacement or rotation. I'm talking about deformation. If you know that there may be the case that large deformation can occur for this body, then maybe a linearized or a linear model may not be enough. Okay? So you can have, for example, Euler beam models, or, for example, Timoshenko beam models, or otherwise higher order models. but this is up to you to choose, for the designer. In this case, we adopted the simplest, probably, model for beam, which is the 1D Euler beam. Okay. Again, this may be confusing for some of you sometimes, but when you talk about 1D Euler beam, it doesn't mean that the information that you get from this model are only living in a one-dimensional model. Okay, what do I mean? When I use a 1D Euler beam, in fact, I can deliver information on the axial and on the transverse, okay, behavior of the beam. Okay, when I say that it's 1D, I refer not to the output, but to the input of the model, because the functional dependence of this model, Euler beam 1D, is only one variable, the length of the abscissa of the beam itself. And that's actually what we see here. So we have two formulas. One for the characterization of the axial behavior, that you can see here, denoted by number 1, and then another which denotes the transverse response. Okay, and again, as you can see, the independent variable here is R0 over bar, only one. That's the only independent variable of all of the overall system, and this is why the model is a 1D model, even if it delivers, again, displacement both in the axial and in the transverse direction, so in the 2D plane. This being accomplished, we have that this choice basically has a direct effect on what? On the displacement field that you can see here. We know that the displacement field U over bar, so the displacement field due to deformation expressed in the local frame, can be expressed in terms of a matrix product between the elastic coordinates, 2F, and a matrix here, which we can actually call Psi, which is the shape matrix. Well, the physics, the choice of the physics of the body directly will influence what happens inside this shape matrix. And this is what we are actually going to see today. For the sake of notation, let's call this, with an overhead, both Psi and QF, but this is just not a general notation, it's just for the sake of clarity in this particular exercise. And you will see and understand why. The other quantities that we need to define all of the physics is, of course, the abscissa. In this case, it's a 1D. So again, you see R0. The R0 vector has just one component. And that's why we won't call it R01 as it should be, but just R0 for the sake of simplicity. And then we have the displacement vector here, U2 and U1 over bar. And of course, we have all the geometric and material information about the beam that we have to know in advance, of course, in order to be able to build the model. Okay. All right, so what we want to do now is to derive, as a first step, to characterize the behavior in the multi-body system of this beam, this body number 3, be able to develop the displacement field. Okay, so let's do it. So this first part is the displacement field. Okay, we have to determine how the this displacement field comes from the choice of the physics for the body. All right, so we have, as I said, two different information for the axial and the transverse physics. Okay, so this is the axial. And we have that this is 0. of course, here we are taking into account the fact that there is no distributed load over the length of the beam. Otherwise, we would have what? Something non-zero here, if you remember the model. This zero means that basically our beam is unloaded in terms of distributed loads. Then there are loads coming from the boundaries. But this zero, if you remember, exemplifies the fact that there are no distributed loads acting in the axial direction of the beam, which is the case. All right. Then, if this is the model that we want to use, I can try to reconstruct a polynomial structure for the displacement of, again, this is the displacement due to deformation. For the axial direction. So we have the Q1 of R0, this is our 1D independent variable, is what? Well, is A0, 1, a constant term, plus A1, 1, okay? So this second subscript here is associated to the direction, while the first one here is associated to the order, okay? So this is the zero order coefficient, and this is the one. Of course, here we have to add this. So this basically, this law here, tells us that the axial displacement must be a linear function, a linear polynomial, right? Because the second order derivative is 0. Okay. Very simple. Let's do the same for the transverse. If you remember, again, we have this, and again, this 0 simplifies the fact that we have no distributed loads in the transverse direction this time. And therefore, from this, we have the following structure. Of the transverse displacement. Okay, if the fourth order derivative is 0, then it must be a cubic polynomial. There is no particular magic here involved. Now, so, you see, this means that if we choose a Euler beam as a model to exemplify the behavior of our body, we have at least 6 coefficients to determine. 6 coefficients. Okay. Now, at this point, we have to, again, take our head back to the notion of the restricted formulation. Did you remember when we talked that one of the problems of the multi-body analysis is represented by the high dimensionality of the elastic problem, right? That in theory, each point of the body can move independently, the one from the other, right? And therefore, it would require an ad hoc generalized parameters to at least one to be able to describe this independent motion. This would require, of course, result in an infinite number of parameters that we cannot afford, of course. So we adopted a restricted formulation, limiting the number to a number n, to our choice, but not infinite. When we do this, we basically are doing what? We are linking the behavior of a point to the neighboring points. This is what we are doing. That's to say, what we do is saying that, you know, the behavior in terms of deformation of a point within our body is not completely independent, but it is related to the one which is featured by some other point within our domain. For example, I can say in our beam, something like this. Okay. What I'm saying is that, for example, the behavior at point A here is not completely independent, but can be, for example, associated, can be extrapolated from the one of, let's see, two other points. Let's call it actually P, for the sake of consistency. This is point P. We have a point A and a point B. And we're saying that A, P, and B, they are not completely independent, so they cannot behave as they want. But that, for example, P, the displacement of point P, is actually a function of the displacement of point A and the displacement of point B. When we enforce this functional dependency of the displacement, we are, of course, limiting the number of parameters needed to completely express this deformation of the body. And this is actually what we do when we, in our restricted formulation, we said that the number of parameters that we needed to describe this deformation was not infinite, but was finite. Okay? Remember, what we said was that U is typically a function of R and T. In theory, it was the sum of infinite terms, Ck, function only of R0, multiplied by a series of QF of T, of K, of course. These were infinite in theory, But now, we are not saying anymore that they are infinite, but they are equal to a number n, finite. And this is the actual consequence of this concept, this restricted formulation, that we are enforcing, again, a dependency of the displacement of points. In another word, we call this what? Discretization of the system. Because we are not talking about a continuous, which is featured by infinite points, but points which are associated the one with the other in a particular way. How? Through the use, again, of these shape functions. This is what we are doing. I guess we have already seen this a lot of times, but this is just to give a context to what we are doing. Why am I talking to this right now? Because we know from what we have derived so far that we need to define at least 6 coefficients to determine the displacement of our beam. Now, the question arises naturally: how many of these pilot points do we want to have in our discretization of the beam? One question can be, we want to have 2. If we want to have 2 of these points, then how many parameters do we have to be able to express for each of these points? I would say 3, right? 3, because we have 6 coefficients. These 6 coefficients will have to be determined by introducing an equal number of elastic coordinates, so we have to have at least 6 elastic coordinates in order to be able to determine this. But if we have 2 points, 2 main points, 2 guiding points, 2 pilot points, then, of course, if we need a total of 6 elastic parameters, they will be, for the consistency of the model, every point must have the same modelization, right? And so we have 3 for one point and 3 for the other point. These 2 points are typically called nodes. Okay. And this was basically very quick recap on the finite element, for example, method, or discretization methods. But this is what we are doing here. So we choose 2 nodes. Okay, and this means we have 3 elastic coordinates for each node. Okay, what are these elastic coordinates? Well, you can again import the image, but just for the sake of clarity, I think it's quite clear. I'm not sure if I can actually crop this figure, but okay, doesn't matter. So you see, we have our QF basically composed of QF1, QF2, QF3, QF4, QF5, QF6. And the description is here, you see. So we have that QF1 and QF4 represent the axial displacement, we're talking about displacements, of point A and point B, so our 2 nodes. QF2 and QF5 represent the transverse displacement. QF3 and QF6, please be aware of this, they do represent not the rotation, but the slope. Okay, the slope. What do I mean with the slope? This is the slope. So if this is the mean axis of our beam, the slope is the following. So for example, let's imagine that we undergo certain deformation, so that the new deformed configuration is like this. Okay, I'm just guessing. So what are the slopes? The slopes are this one. It's exactly the tangent of point A and point B. Okay, so basically we have that. Just to be clear, that we have a certain, this is the slope, and we can call it basically U2 prime, or if you want, just to be clear, d U2 or dr0 bar at point A. This is also called U2 prime at A. This is QF3. Okay, this is clear? Okay. And the same, of course, goes for point B. So the U2 for dr0, which you can also call U2 prime at this point at B. Yes, this is QF6. The completion of this was what it is that U1 at point A is, you see, it's QF1. The transverse always at point A is instead QF2. This is just by definition. Of course, you can have also alternate definition as long as they are 6 and they are linearly independent. But you can choose whatever you want. But this is the most obvious, I would say. And the same goes, for example, for point B. This is QF5, if I'm not, no, QF4. Yeah. Yeah. And then QF5. Okay. All right. Now, what we have to do is, okay, this is all very nice, but how do we actually eventually determine our coefficients? We have to impose the boundary conditions. Okay. We have to impose, in fact, said more properly, we have to impose that our coordinates deliver the exact information given this definition at the nodes. So meaning this, what we have to do is reinforce these definitions given the so we enforce this definition given the structure of the displacement that we have in star, where star is this. Star is this, basically. Let's call it like this. Okay. So what do I mean is that we have this definition of the displacement, this polynomial definition. Then we define the elastic coordinates in this way. This way here. And now what I want to determine is the coefficient in enforcing these definitions. It's more actually, it's harder to say than to do it. So what is it that we do? We have the following. So U1 at 0 is what? Well, is A01, given the polynomial expansion that we have done. And this is by definition, QF1, right? Okay. The same goes, of course, for point Y0, because this is point A. R0 is equal to 0 at point A. While at point B, which is at the extremity, the other extremity of the beam, R0 equal to L, this is equal to what? It's A01 plus A11 times L. This is by definition equal to QF4. Okay, and this is for the axial behavior. All right, let's do the same, of course, for the bending. For the bending, what we have is, again, U2 at 0, and this time is A02 This is by definition QF2. Okay. And then again, U2 at L is A02 plus A1 to L plus A2 to L plus A3 to, sorry, L square and cube. And this is by definition QF5. Okay. And then we have the slope. U2 prime, the derivation of the slope, if you want, at 0. This is A12. Okay. And this is, by definition, again, what we have called QF3. And the same goes for point L, point B. In this case, we have A12 plus 2 times A2 to L plus 3 times A3 to L squared. And this is again, by definition, equal to QF6. Okay. And all of this is the transverse or bending okay. You see here, you have a system basically of 6 unknowns, which are the coefficients, expressed in terms of 6 parameters, which are our coordinates. So what I'm doing here, you have to understand this. This is the logic of this operation. We are reparametrizing the problem. What do I mean? First, in here, the problem is expressed in terms of the coefficients, A1, A2, A3, blah, blah, blah. Now I want to express this in terms of elastic coordinates, Q1, Q2, Q3, Q. Okay, this is what I'm doing. So I want to relate the displacement of each point in our body to the displacement of 2 points, which I call nodes, as a direct effect of the restricted formulation. All right. If you solve the problem, solving the system, we have the following. I spare you all the algebra, and we have the A01 is equal to QF1. Okay. Then we have that A11 is equal to QF1 minus QF4, sorry, QF4 minus QF1 divided by L. Okay. In fact, dimensionally wise, it's okay, no? Because this is A01 is the constant term in the polynomial expansion, while A11 has to be multiplied by R0. So dimensionally, you see, you have an L. So these are all, reasons that you can go through to see if what you're doing is okay or not. All right, then we have A02, and this again, you see, it's QF2. Then we have A12, and this is QF3. Then we have A22, a little bit more complicated here. It's 3 times QF5 minus QF2 divided by L squared minus QF6 plus 2 times QF3 divided by L. Okay. So you see, I'm expressing the coefficients in terms of the elastic parameters. And then the last one, 2 times QF2 minus QF5 divided by L to the third plus QF3 plus QF6 divided by L squared. Okay. All of these will allow us to write the following. That U1, now if I basically substitute this expression of the coefficients into our polynomial expansion, what we get is the following. Is 1 minus C times QF1 plus C times QF4, where C is just R0 over divided by L. Okay, it's just, to make it non-dimensional. So this is, you see, what we have a01 times plus a11 times R0. Now it's this one. You see, expressed instead of being expressed in terms of these two. Now we have it expressed in terms of QF1 and QF4. Okay, we have reparameterized the problem. That's all we did. And the same, of course, goes for the transverse counterpart. Okay, let's actually do it like this. So U2 is a little bit more complicated, but nothing really impossible. 1 minus 3 times C to the second plus 2 times C to the third times QF2 plus L multiplying C minus 2 C to the second plus C to the third. Here we have QF3. And then we have 3C squared minus 2C to the third. All of this is being multiplied by QF5. Let me just rewrite it this later. Plus L multiplying C to the third minus C to the second times QF to the QF6. Let's rewrite it here. Okay. So you see now you have this expression of U1 and U2. So the transverse and the axial displacement. Now, I want to put all of this in a matrix form. Let's do it so. So, matrix form. Oops. So in matrix form, we have U1, U2, equal to what? Something that has to multiply what? Our vector of elastic coordinates. QF3, QF4, QF5, QF6. So this is a 6 times 1 vector. This is a 2 times 1. Of course, this must be what? A 2 times 6 matrix. Let's fill it out with the expression that we have seen before. Well, if we do it, it's 1 minus c, then we have 0, 0, c, 0, 0. And in fact, if you multiply this first row of the matrix with the column, you get U1 over bar. Let's do the same for the second row. And what you get is the following. This is the second element. Then we have the third element. C minus 2c to the second plus c to the third. Okay. Then we have a 0. And then we have, let me write like this, so that we don't get confused. So these are all different terms. Okay. Then we have 3 c to the second minus 2 c to the third. And then the last one. L c to the third minus c to the second. Okay. Now, if you look at this expression, and you compare it to the one that we had at the very first slide, this is basically U. This is exactly C overhead, and this is QF overhead. Sorry, but I don't remember if I wrote it just for the sake of consistency. Yeah, I put a net also in there, so it's fine. Okay, so what we have done here is determining this psi overhead matrix, but this psi overhead matrix is not yet the final shape matrix. It's not yet the final one, and that's actually why we have introduced this overhead, as I told you in the beginning of this exercise. Why? Because in this formulation, we can, this formulation, in theory, should represent what? U overhead, your overbar here. And these are displacement induced by deformation. So there should be no rigid motion in here. Okay? But now we will demonstrate that this formulation, in fact, includes also rigid motion in this expression of U. So there is something that is not quite right. Okay? So let me, this is the deformation induced displacement. So this means that no rigid motion should be included. Okay. But we will see that this is the case, in fact. Actually, there is a rigid motion inside. No? And let's check it out. Okay, let's say, for example, that we can divide our QF1 into two different contributions. QF1 elastic plus a rigid term, D. Okay? So, this is elastic. And this is rigid. Okay? We also do the same for QF4. So now we, for the sake of simplicity, now here we demonstrate it only for the axial behavior, no? Because it's easier. But the same can be done also for the transverse. Okay, so you will have that again. This is QF4 elastic plus the same. Okay. So it means that if you let me exemplify the beam as a 1D body, if this is A, this is B, we have this first displacement, this is D, this is B, and then there is, for example, I don't know, this is QF1 elastic, okay, and then there is, I don't know, just to make it sure, QF elastic for A. So that our new deformed beam is the new AB. Okay? So you see, there is a rigid part in this displacement, and then there is an elastic one. This is undeformed or initial, and this is the actual configuration of the beam. If we do this, our U1, our expression of U1 becomes the following. So I substitute this into the expression of U1, and it becomes as follows. Q F1 elastic plus 1 minus C, and then we have Q plus QF 4 elastic times C, and this is very similar to what we have done, plus B. You see? This means that what is supposed to be an axial displacement only due to deformation. In fact, has a component which is rigid. Huh? And this is we don't want that. Because, again, these U over bar, as we have already know, only are expressing the displacement due to deformation. So this will the axial displacement U1 supposedly due only to deformation, actually contains a rigid term. Okay, and we don't want that. So we have to get rid of that. How do we get rid of that? We impose the so-called reference conditions. This is something that you do not see when you I think, when you go through the formulation of, for example, finite element model. Do you actually see this thing? That when you do the formulation, in fact, there is a rigid motion included? I don't think so, and you know why? Because typically the structural problems that you see in previous courses, they do not encompass a rigid motion of the body. Okay, so you only are instructed for the elastic behavior. So you have a beam, a cantilever beam, for example, that has a fixed boundary, and then the other end is free, and then it can deform. And then you don't have interest in taking this problem into consideration. No? The problem that the body can move freely, rigidly in the space. But in our case, we do, because in our multi-body problem, bodies can fly in the space and then can deform as well. So we do have to take into account into this thing. Otherwise, if you do not pay attention into discriminating this thing, we will consider this displacement 2 times. One in the displacement due to deformation, and the other one in the rigid counterpart. Because if you remember, we have that our displacement, for our position, sorry, was basically composed by, you see, already we have a translation, and then we have if you remember now. So you cannot take into account the D here and here as well. It would be a mistake. That's why we have to get rid of this here. You understand why we are doing this now? Otherwise, we would account for it 2 times, and that's not good. So how do we get rid of this? We have to enforce the so-called reference condition. These are very important. What are these reference conditions, in fact? These reference conditions are what we have talked about yet when we discussed about the fact that in case of a deformable body, the relationship between the local frame and the body is not so obvious as in the rigid case. In the rigid case, you have a local frame, it's attached to the body, and you forget about it. But when the body can deform, how do the local frame follow this deformation? It's not a trivial question. And we said, if you remember, that you have to lock somehow the frame with respect to the body, so that the relationship between the frame, the local frame, and the body was unique. Okay? So that the displacement in the body, expressed with respect to the local frame, are univocally defined. Well, this relationship that lock the local frame with respect to the deformable body are called the reference conditions. And they are arbitrary. Okay? So I can make a choice, you can make another choice, and they can both be valid as long as they are linearly independent and they deliver a correct expression of the local displacement with respect to the local frame. Okay? In a unique way. This is what I mean with correct. Okay? For the case at hand, how can we enforce these reference conditions? If you look at the this picture here, we are modeling the beam AB. So one way to do that would be, for example, saying that the body AB within our assembly behaves like what? Like a simply supported beam. Meaning that at the edges A and B, there can be no relative motion in this direction, relative motion, not in this direction, or in this direction. There can only be a rotation, and here as well, at least. Okay, so we have three conditions. So it means that the body 3 with respect to the body 2, it cannot move. There cannot be a relative motion at point A, only rotation, relative rotation between body 2 and 3, and only a rotation, again, and in this case instead, yes, you can actually have an axial motion here, you can, with respect to body 4. Okay, so it's a simply supported beam. So that you have something like this. Here you have a hinge, like this, and here you have a hinge with a tray. Otherwise, the system would be hyperstatic, no? You would constrain it too much. So you have to eliminate this degree of freedom, this degree of freedom, and this. Okay. If you do this, you will remove that rigid motion that we have detected, this D here. Okay, so you have to lock your body within your assembly. So, to sum it up, we consider our link, we call it link because it's a common term, as a simply supported beam within our assembly. Okay? Again, this point A. This point B. So this means that u1 over bar at 0 must be 0. That u2 over bar at 0 must be 0. And that u2 at L must be 0 as well. Okay? And this translates into what? It translates into the fact that QF1 must be 0. That QF2 must be 0. And QF5 must be 0. Now the question is, how do I actually encompass? How do I introduce this condition within our model? I do the following. I say that the only remaining elastic parameters that we have here are QF3, QF4, and QF6, right? All the other ones are set equal to 0. Then we say that these are equal to matrix times QF1, QF2, QF3, QF4, QF6, QF5, sorry, QF6. Okay. How do we actually relate these two? Well, it's quite easy, no? We have 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, and eventually 0, 0, 1. Okay? So we basically are restricting our vector of elastic coordinates from the general one to the actual one. Why? Instead of one way, if you want, one way of enforcing this, because they have to be 0, is actually removing them from the formulation. Because you cannot set it as a variable anymore. Okay? So I started with a 6 vector parameter, because as we remember, we needed 6 parameters in order to be able to define the 6 coefficients. But eventually it turned out that I have to set this condition to avoid rigid motion. And one way to set this rigid motion, to set this condition, is downsizing my vector of elastic coordinates to this one. Okay? This is a way to enforce them. And this is written as QF equal to n, this matrix over bar, times QF over bar. You see? And that's why we introduce the overhead at the beginning of the exercise. Because the actual vector of elastic coordinates, what do I mean with actual? The one that I actually can arbitrarily define is just this one here. Why? Because some of these I cannot arbitrarily define. They are not unknown variables. They are not the unknown variables of my problem anymore, because I have to enforce these conditions. Okay? Again, one way to enforce this condition is again downsizing my vector of elastic coordinates. Okay, so this is basically my QF, my vector of QF, is my N over F, and this is my QF over F. Okay. The last passage of this, can I slide? Mm-hmm. No. Avete ragione, sì. Sì, scusate. Sorry, I omitted this. Transpose. Okay. No. Sorry. Okay. No. I made a mistake. No, I made a mistake, sorry. It's the other way around. So it's all transposed. Huh? So we have the following. It's actually like this. Yeah. So it's actually like this. Hmm? Okay. Of course. And it is 0, 0, 0, 0, 0, 0, 1, 0, 0. Of course, otherwise you could have not done the multiplication, of course. Okay? Thanks. Now the last passage, and then we are done with this, is the following. We can write U is equal, again, as we have said, to psi QF, but QF is equal to psi N over H times QF. Okay, and this, we have the final expression of the shape matrix, which is this one. So that my psi is equal to psi over H times N. And this is, if you remember, was a 2 times 6. This is a 6 times 3. And so here you have a 2 times 3. So my final expression of the shape matrix is the following: 0, C, 0. If you multiply, if you do this matrix multiplication here, which is trivial, you get the following. There you go. Okay. So you see, now we have determined the shape matrix. In this shape matrix, we have basically what? We have condensed the physics of our body. So the way it deforms, namely our Euler model, 1D Euler model of beam, is all included here. And in this case, there can be no rigid motion. No rigid motion is anymore included. So all that you get here now is deformation induced displacement. Okay. Okay, so this basically concludes today's lecture. The last, well, let's see, the last minutes of today's lecture, I would dedicate them to the completion of the QUID questionnaire. I don't know if you've already gone through it. So, let me just stop the recording.